In this lecture, I will explain the phenomena Bose Einstein condensation. This is a phenomena showed by a system composed of particles which obey Bose Einstein statistics. In the last lecture, we started our discussion of thermodynamics of ideal Bose gas, and we have the following two equations. The first one was P by kT is equal to 1 by lambda cube G 5 by 2 of Z. Here, lambda is thermal de Broglie wavelength and it is given by h divided by root 2 pi m kT, and Z is the fugacity of the gas and it is related to the chemical potential through the relation E raised to mu by kT. Okay? P is pressure, K is Boltzmann constant, and T is absolute temperature. And the second equation was n minus n0 divided by V is equal to 1 by lambda cube G 3 by 2 of Z. Here n is the total number of particles in the system. N0 is the number of particles in the ground state, that energy with state with energy E equal to 0. V is the volume of the system. And these two functions g 5 by 2z and g 3 by 2z are Bose Einstein functions, and the general definition of Bose Einstein function is g nu of z is equal to z plus z square divided by 2 raised to nu plus z cube divided by 3 raised to nu plus etc. Okay. In principle, the maximum value of z is 1. So the value of z is always less than or equal to 1. Therefore, the value of g 3 by 2 of z is also limited. We can find the maximum value of g 3 by 2 z, and it is nothing but g 3 by 2 of 1, because the maximum value this variable can take is 1. So that value will be 1 plus 1 by 2 raised to 3 by 2. Instead of nu, we have 3 by 2 plus 1 divided by 3 raised to 3 by 2 plus etc. This value is actually 2.612, and we can denote it as theta of 3 by 2. This value is 2.612. This is the maximum value that this function g 3 by 2 of z can take. Okay. Since this value has a limit, that implies n minus n0 by v should also have a limit. Okay. That is, we can write the maximum value of n minus n0 by v. That is, I can write it as Ne by v, because n is the total number of particles, n0 is the number of particles in the ground state. So n minus n0 gives the value of number of particles in the excited state, and that is nothing but g 3 by 2 of z divided by lambda cube, where lambda is the mean thermal de Broglie wavelength. Okay, so from this equation we can say that Ne maximum is V by lambda cube into g 3 by 2 of z maximum, and the maximum value of g 3 by 2 of z is nothing but 2.612. So we can write Ne maximum is V by lambda cube into 2.612. This is the maximum number of particles that can occupy the excited states in the case of a Bose gas. In the case of a Bose gas, that is a system consisting of particles which obey Bose Einstein statistics. This is the maximum number of particles that can occupy the excited states altogether. Okay. If the total number of particles in the system is less than this maximum value, then practically all particles will be in the excited states. all particles will be in the excited state and there is no issues. We can find the actual value of Z using the expression Ne is equal to V by lambda cube G 3 by 2 of Z. Okay, Z is given by this expression by replacing Ne with N. Okay, because the total number of particles now is less than the limiting value. There is no restrictions. So the particles can occupy the excited states because excited states can hold these many particles. But now the total number of particles in the system is less than this value. So that all the particles can occupy the excited states. And you can find the exact value of Z using this expression by replacing this Ne with the total number of particles in the system N. Okay, so that will give you the actual value of Z. But what happens if the total number of particles in the system is greater than this maximum value of Ne? Okay, if the total number of particles in the system is greater than the limiting value Ne max, then the Ne max number of particles will occupy the excited states. Okay, this is the maximum number of particles that can hold by the excited states. So those particles will be there in the excited states. Any maximum number of particles will occupy the excited states. The remaining particles, that is N minus Ne maximum, that has to go to the ground state. Okay, or these many particles will be pushed to the ground state because the maximum number of particles that can occupy the excited states is given by this number Ne maximum. It is limited, so the remaining particles N minus Ne maximum will be pushed to the ground state. And the ground state is actually the number of particles in the ground state is unlimited. Will be pushed into the ground state. Okay. So this phenomenon is known as Bose Einstein condensation. Okay. If the number of particles in the system is larger than the limiting value Ne maximum, the remaining particles N minus Ne maximum will be pushed to the ground state and there will be an accumulation of particles in the ground state, and this phenomenon is known as Bose Einstein condensation. The number of particles in the ground state is given by the relation N0 equal to N minus Ne maximum, and it is nothing but V by lambda cube into 2.612. This is the maximum value of number of particles in the excited states. Total number of particles in the system is N. So N minus this quantity will give you the number of particles in the ground state. And here Z value can be calculated. Z can be calculated by using the formula, by using the equation Z is equal to N0 divided by 1 plus N0. This equation actually obtained from the occupation number. We have for the occupation number of a state with energy epsilon, that is given by N epsilon is equal to 1 divided by Z raised to minus 1 E raised to beta epsilon minus 1. This is the occupation number of energy level with energy epsilon in the case of a system consisting of Bose particles. And the occupation number of ground state is given by replacing this epsilon with 0, that is simply 1 by Z raised to minus 1 minus 1. And this is nothing but 1 by Z minus 1. So this is Z by 1 minus Z. This occupation number of the ground state is nothing but the number of particles in the ground state. So I can write N0 as Z by 1 minus Z, and you can rewrite this like n0 minus n0z is equal to z, or n0 is equal to z into 1 plus n0. Therefore, z is equal to n0 divided by 1 plus n0. So, if the number of particles in the system is greater than the limiting value, Ne maximum, there will be accumulation of particles in the ground state, and that number of particles is given by n0, and the actual value of z you can calculate using this expression n0 by 1 plus n0, and you can write this as approximately equal to, you can take n0 from both numerator and denominator and you can cancel it, then the remaining is 1 divided by, this is equal to 1 divided by 1 plus 1 by n0, and using binomial expansion, if you retain only the first two terms, it will be something like 1 minus 1 by n0, 1 minus 1 by n0. But the value of n0 is very large, value of n0 is very large, so set is nearly equal to 1. Since n0 is very large, the value of z is very nearly equal to 1. It is always less than 1 because 1 minus a factor, but this factor is actually very small. So z is approximately equal to 1 when the number of particles in the system is greater than the limiting value. Okay. Now we can find the condition for the onset of Bose Einstein condensation. Okay, condition for the onset of Bose Einstein condensation. Actually, we can write different conditions. Different conditions means different conditions in terms of temperature, or in terms of number of particles, or in terms of volume, etc. Okay. So already we have the condition in terms of number of particles. If the number of particles in the system is greater than V by lambda cube into 2.612, we will have the phenomenon Bose-Einstein condensation. If the number of particles in the system is greater than this value, we will have the phenomenon Bose-Einstein condensation. And I can write this condition as V into lambda cube is actually h cube divided by 2 pi m kt raised to 3 by 2 into 2.612. Okay, lambda cube is in the denominator. Its value is h cube divided by 2 pi m kt raised to 3 by 2. That factor will go to the numerator. So this is the condition for the onset of Bose-Einstein condensation. That is, the number of particles should be greater than this value. That is, for a fixed volume V and fixed temperature T, if we have the number of particles n greater than this value V by h cube 2 pi m kt raised to 3 by 2 into 2.612, we will have Bose-Einstein condensation. This is the condition for the onset of Bose-Einstein condensation in terms of number of particles in the system, keeping volume and temperature fixed. Now you can think of keeping the number of particles and volume fixed. We can find the temperature. We can find the temperature for the onset of Bose-Einstein condensation. So from this equation, you can see that that condition is T raised to 3 by 2 should be less than n. Here you have n, you can take this h cube to the numerator, and 2 pi mk raised to 3 by 2 will go to the denominator, and there is a 1 divided by 2.612 also. So if t raised to 3 by 2 is less than this quantity, you take all these quantities to the left hand side, then the condition is t raised to 3 by 2 less than this number, then again you will have Bose-Einstein condensation. So I can say that T less than, if I write it like h square divided by 2 pi mk, N by V, you have a V also. Here you have a V, so that will be in the denominator. N by V raised to 2 by 3. 1 by 2.612 raised to 2 by 3. This is the condition for the onset of Bose-Einstein condensation in terms of temperature. In terms of temperature, this temperature you can denote it as Tc, the critical temperature, and it is given by h square divided by 2 pi mk small n raised to 2 by 3, where small n is the number density of particles, 1 divided by 2.612 whole raised to 2 by 3. Okay, this is known as critical temperature. This is known as critical temperature. If the temperature of the system is below Tc, if temperature of the system is below Tc, we will have Bose-Einstein condensation. We will have Bose-Einstein condensation. That is the condition for the onset of Bose-Einstein condensation in terms of temperature. And the important points to be noted is that temperature, critical temperature is proportional to 1 by m, depends on the size of the particles in the system, and it also depends on the number density of particles. Okay, as the number density of particle increases, the critical temperature also increases. So this is the condition for the onset of Bose-Einstein condensation in terms of temperature. So we can say that if the temperature of the system is less than this critical temperature Tc, the system has two phases. Okay, the system may be looked upon as a mixture of two phases. The first phase is a normal phase consisting of any particles that is distributed over the excited states means the states with epsilon not equal to 0. And the second phase is a condensed phase consisting of n 0, that is given by n minus ne particles in epsilon equal to 0 state, that is the ground state. Okay, so for t less than Tc, we will have particles in excited states as well as in the ground state. So we can say that the system has two phases. One is a normal phase consisting of Ne particles distributed over the excited states, and the second phase is a condensed phase in which n0 equal to n minus Ne. Total number is n. Ne particles are in the excited states. So in the ground state, you will have n minus Ne particles. And the ground state is nothing but epsilon equal to 0 state. Now, what is the value of Ne? Ne is given by V. Ne is given by V divided by lambda cube into 2.612. This I can write it as Ne is equal to V into 2 pi mk raised to 3 by 2 divided by h cube into 2.612 into t raised to 3 by 2. But we have an equation for t raised to Tc raised to 3 by 2, Tc raised to 3 by 2. What is Tc raised to 3 by 2? You have Tc equal to this equation. So Tc raised to 3 by 2 is h cube divided by 2 pi mk raised to 3 by 2 and n by v into 1 by 2.61. So you can replace these quantities in this equation for Ne, and you can write Ne as n into T by Tc raised to 3 by 2. T by Tc raised to 3 by 2. Because instead of these quantities, h cube divided by 2 pi mk raised to 3 by 2, n by v into 1 by 2.612. You can substitute as Tc raised to 3 by 2. Then this v will cancel, there will be an n, and these all terms will cancel. So finally, you will get it as Ne is equal to n into T by Tc raised to 3 by 2. n into T by Tc raised to 3 by 2. And therefore, this is for normal phase, this many particles in the excited states. Condensed phase with n0 equal to n into 1 minus T by Tc raised to 3 by 2. These many particles in the ground state. This is the condensed phase and this is the normal phase. And we can draw a plot. We can draw a plot which is given by this. In the x-axis, you have T by Tc. In the y-axis, we have n0 by n and ne by n. This red color shows the n0 by n plot, and this green one shows the ne by n plot. This 1 means T equal to Tc. T by Tc is 1 means T equal to Tc. So below T equal to Tc, you have two phases. This red one and green one. Above T equal to Tc, you have only one phase, that is the green one, that is Ne by N. Okay? So beyond the critical temperature, there is only one phase, the normal phase. But below the critical temperature, Bose Einstein condensation occurs, and you will have a mixture of two phases. One is the normal phase, and the normal phase, the number of particles in the excited state goes on decreasing as temperature decreases, and the number of particles in the ground state goes on increasing as the temperature increases. At T equal to 0, what happens at T equal to 0? If you look at this expression, at T equal to 0, this Ne is effectively 0 and N0 is effectively N. The total number of particles, all the particles will occupy the ground state. All the particles will occupy the ground state and you will have only the condensed state. Okay. There is no normal phase. And as T tends to Tc, what happens? As T tends to Tc, this Ne is approximately equal to N and N0 will be 0. N0 will be 0. That is, as the temperature tends to critical temperature, the particles will occupy the excited states. The number of particles in the ground state will be 0. That is the nature of this graph. I think it is clear. Okay. Now, we will look into the variation of Z with the temperature. Okay. Instead of considering directly the variation of Z with the temperature, we will consider variation of Z with V by lambda cube, where V is the volume per particle. Okay. And this V by lambda cube is proportional to T raised to 3 by 2. So the variation of Z with V by lambda cube will give you the variation of Z with the temperature. Now, we will consider three different areas. One is the region in which temperature is between 0 and critical temperature Tc. When temperature is 0, this V by lambda cube will also be 0. Because V by lambda cube consists of T raised to 3 by 2, a term T raised to 3 by 2. When temperature is 0, this V by lambda cube is also 0. So that limit is 0. When T equal to Tc, what is the value of V by lambda cube? In order to calculate that, you consider the expression for critical temperature. Tc raised to 3 by 2 is h cube divided by 2 pi mk raised to 3 by 2 into n by v into 2.612. And this n you can take to the denominator so that v by n becomes small v, and h you can multiply and divide with T raised to 3 by 2, then you will get this term as lambda cube, and there will be a T raised to 3 by 2 in the numerator. Okay, so when T equal to Tc, this Tc raised to 3 by 2 and this Tc raised to 3 by 2 will cancel, and you will get the value of V by lambda cube as 1 by 2.612. So we got the two limits. When T equal to 0, V by lambda cube is also 0. When T equal to Tc, V by lambda cube is 1 by 2.612. So T between 0 and Tc implies that V by lambda cube between 0 and 1 by 2.612. What happens in this range? In this range, there is the condensed phase and the number of particles in the ground state is very high. So the Z value is calculated using this expression N0 by 1 plus N0, and we already discussed this equation. It is given by approximately 1 minus 1 by N0. Since N0 is very large, you have Z approximately 1. So for all temperature below the critical temperature, the value of Z is approximately 1. Value of Z is approximately 1. Now what happens when V by lambda cube is greater than 1 by 2.612? That is temperature greater than critical temperature. Then the value of Z will be less than 1. And we can calculate that using this relation. N by V is equal to 1 by lambda cube G 3 by 2 of Z. We have this relation. So we can write as G 3 by 2 Z equal to lambda cube by V. And V by lambda cube greater than 2.612 means lambda cube by V less than 2.612. So G 3 by 2 Z less than 2.612. That is the condition. G3 by 2 Z by definition it is given by Z plus Z square by 2 raised to 3 by 2 plus Z cube by 3 raised to 3 by 2 plus etc. up to infinity. For this value should be less than 2.612. We know that when Z equal to 1, this left hand side will give you 2.612. Okay, in order to get a value less than 2.612, Z should be less than 1. Because the maximum value of Z is 1. For that value, you will get the left hand side sum as 2.612. In order to get a sum which is less than 2.612, you should have Z less than 1. Therefore, when V by lambda cube greater than 1 by 2.612, Z value is less than 1. That is the second region. Now, the third region, V by lambda cube greater than 1. When the value of V by lambda cube is greater than 1, from this equation, we can say that G3 by 2Z is less than 1. Okay, from this equation, when V by lambda cube greater than 1, G3 by 2Z will be less than 1. G3 by 2Z, that is this infinite sum. This is less than 1 implies Z should be less than 1. Okay, and when this quantity Z is very small, you can neglect all the higher order terms and you can write G3 by 2Z approximately as Z. You can retain only the first term. Therefore, you can write Z approximately as G3 by 2Z, and that is nothing but V by lambda cube raised to minus 1. Actually, G3 by 2Z is lambda cube by V. So, you can write it as V by lambda cube raised to minus 1. Okay. So, what is the classical limit or classical value of Z? In the case of classical statistical mechanics, we find that in the case of grand canonical ensemble, we calculated the Z value and we obtained it as n lambda cube, and this is exactly that value because this V is actually 1 by n. So, this is exactly Z is equal to n lambda cube. So, all is in agreement with the classical result. So, in the limit t very large or t tends to infinity, that is the meaning of V lambda cube greater than 1. So, in the limit t tends to infinity, Z value fugacity is given by n lambda cube and it is the classical result. So, I can plot this fugacity here versus V by lambda cube. This is a plot of Z versus V by lambda cube up to 1 divided by 2.612. That is between a temperature 0 and Tc. Z value is almost 1. Z value is almost 1. This is the first region. Between 0 and Tc, that is between a value of V by lambda cube 0 and 1 by 2.612, you have Z value approximately 1. As V by lambda cube is greater than this 2. When this V by lambda cube is greater than 1 by 2.612, then Z is less than 1. That is why in this region Z is less than 1. Now, in the limit V by lambda cube greater than 1, that is T tends to infinity. In that range, this Z value is V by lambda cube raised to minus 1. That is when V by lambda cube is 2, Z value will be 0.5. When V by lambda cube is 3, Z value will be 1 by 3 and so on. Okay, that is the variation of Z with respect to V by lambda cube. Okay, Z is constant and it has value 1 up to 1 by 2.612. Beyond that, it starts decreasing, and for very large value of V by lambda cube, it has a 1 by x dependence. It has a 1 by x dependence. Okay, so that is why we said that for temperature greater than critical temperature, N0 is 0. Okay, for T greater than Tc, we have N0, the number of particles in the ground state is effectively 0 because N0 is given by Z divided by 1 minus Z, and for T greater than Tc, this Z value is less than 1. If you take Z value as say 0.9, what is N0? N0 will be 9 if you substitute in this expression. This value is negligibly small compared to the total number of particles in the system. It is of the order of 10 to the power 23. And you can effectively say that the ground state population is 0. Number of particles in the ground state is 0. If Z is 0.99, then also this value is roughly 99. Okay, that is again negligible compared to the total number of particles. That is why in this graph you have beyond the critical temperature, number of particles in the ground state is effectively 0. Okay, so that is the variation of Z with the temperature. Now we will discuss about the PT diagram for a Bose gas. We have the expression P by KT is equal to 1 by lambda cube G 5 by 2 of Z. Actually, we started this lecture with this expression. And for T less than Tc, we already proved that Z is approximately 1. So this G 5 by 2 of Z becomes G 5 by 2 of 1. We can denote it as theta of 5 by 2. Theta of 5 by 2. Therefore, P of T is equal to, this KT will go to the right hand side, KT by lambda cube theta of 5 by 2. This equation is valid when T less than Tc. This implies P is proportional to T raised to 5 by 2 because in lambda cube there is already a 1 by lambda cube, there is already a T raised to 3 by 2, there is another T here, so that becomes T raised to 5 by 2. Okay, so the important observations are pressure below the critical temperature is proportional to T raised to 5 by 2, and the second one is pressure is independent of V by N or volume per particle. Okay, pressure is independent of volume per particle. That means infinite compressibility. Okay, you can compress the gas to any extent. There is no limitation for volume per particle. So you can increase pressure to any value. That means infinite compressibility. Now, at T equal to Tc, you can substitute this T as Tc. Then P of Tc equal to 2 pi m by h square raised to 3 by 2 k Tc raised to 5 by 2 theta of 5 by 2. This is obtained by putting the value of lambda cube and replacing T with the Tc. Because up to T equal to Tc, that value is 1. Okay, there is no issue for using this relation. So pressure at a critical temperature is given by 2 pi m by h square raised to 3 by 2 KTc raised to 5 by 2 theta of 5 by 2. But we have Tc raised to 3 by 2 is equal to h cube divided by 2 pi mk raised to 3 by 2 n by v into theta of 3 by 2. Okay, so you can write P of Tc as KTc into n by v theta of 5 by 2 by theta of 3 by 2. Okay, theta of 5 by 2 by theta of 3 by 2, this is a numerical value and its value is 0.5134. The remaining terms are nkt by v. So pressure at a critical temperature is 0.5134 nktc divided by v. But Tc is the critical temperature. Pressure is given by P of Tc. N is the number of particles. V is the volume. K is Boltzmann constant. You know that for an ideal gas, PV equal to NKT. For an ideal gas, PV equal to NKT or P is NKT by V. But for a Bose gas at the transition temperature, the pressure is only one half of the pressure of an ideal gas. For an ideal gas, pressure is nkt by V at any temperature T. For a Bose gas at a critical temperature, pressure is one half of the pressure that is exerted by particles of an equivalent Boltzmannian gas, that is an ideal classical gas. Okay. Now, for T greater than Tc, these equations are applicable only up to T equal to Tc, because we took Z approximately as 1. But for T greater than Tc, Z is not 1, Z value is less than 1. So, you have to use the actual expression P by Kt equal to 1 by lambda cube G 5 by 2 of Z. You cannot replace this Z with 1. For T less than Tc or for T equal to Tc, you can replace this Z with 1. For T greater than Tc, you have to write it as Z itself. Also, we have n by V equal to 1 by lambda cube G 3 by 2 of Z. Actual expression was n minus n0 by V. But for T greater than Tc, n0 is effectively 0. Therefore, n by V equal to 1 by lambda cube G 3 by 2 of Z. You can divide these two expressions in order to write P equal to n by V into Kt G 5 by 2 Z by G 3 by 2 Z. An exact evaluation of this is very difficult, but in the limit T tends to infinity, you can calculate the value. Okay. If T is very high, the limit T tends to infinity, Z will be very small, and G 5 by 2 Z you can approximately write it as Z. G 3 by 2 Z also you can approximately write it as Z. Then that will cancel both in the numerator and denominator. You will get P equal to nkt by V. The exact equation that obtained for the Boltzmannian gas. Okay, so this is the plot of PV by NKTC versus T by Tc. And this red line shows the graph of P equal to KT by lambda cube theta of 5 by 2. Okay, this red line is the graph of P equal to Kt by lambda cube theta of 5 by 2. Theta of 5 by 2. That is, this is valid only up to T equal to Tc. That is only up to T by Tc equal to 1. Okay, a Bose gas will obey this line only up to this point. Only up to this point. Actually, this green one is the graph of Bose gas. This red one is the equation P equal to Kt by lambda cube theta of 5 by 2. It is actually called the transition line. And this green one is the graph of Bose gas. Green one and red one are exactly the same up to T equal to Tc. Beyond T equal to Tc, the Bose gas deviated from the transition line and it asymptotically tend to the limiting value Pv equal to Nkt. This straight line is Pv equal to Nkt. That is the graph for Boltzmannian gas or classical ideal gas. This Bose gas tends to that value in the limit T tends to infinity. Beyond T equal to Tc, it satisfies this equation. So, this green curve and the red curve are exactly the same up to T equal to Tc. Beyond T equal to Tc, the Bose gas departed from this transition line and it tends to the classical behavior at T tends to infinity. Now, this red line is actually the graph of P equal to Kt by lambda cube theta 5 by 2. That is P proportional to T raised to 5 by 2. Okay, this is a graph of P proportional to T raised to 5 by 2. Now, the right of transition line is normal phase alone. The right of transition line, that is this portion. The right of this red curve is the normal phase alone. On the curve, the transition line itself shows the mixed phase. That is normal phase plus condensed phase. And the left of transition line is the forbidden region. That is not possible. Okay. So, right of transition line is normal phase alone. The line represents mixed phase. Left of transition line is not accessible. Okay. I will explain. For T less than Tc, we will have mixed phase that we already studied in the case of Bose gas. When the temperature is less than critical temperature, we will have two phases, normal phase and condensed phase. And for t less than Tc, we already know that this equation is valid. P equal to Kt by lambda cube theta of phi by 2. And that red line in the graph is exactly that equation. So this red line shows the mixed phase. Okay, this red line is applicable for t less than Tc. So that red line shows the mixed phase. Mixed phase. For t greater than Tc, we will have normal phase alone. Okay, from the definition, when t greater than Tc, there is total number of particles is less than that maximum number of particles that are occupy the excited states. So we will have only normal phase. There is no condensed phase. Then the equation for P is given by Kt by h cube 2 pi m Kt raised to 3 by 2 g 5 by 2 of z. Okay. For t less than Tc, we will replace this z with 1. But for t greater than Tc, you have to keep it as z itself. Also, g 5 by 2 z is less than theta of 5 by 2. G 5 by 2 z is less than theta of 5 by 2. Theta of 5 by 2 is the value of g 5 by 2 z by putting z equal to 1. For any value of z less than 1, that will be less than that maximum value. So that means Pt raised to minus 5 by 2. This t and this t raised to 3 by 2 becomes t raised to 5 by 2. When you take it to the left hand side, that becomes Pt raised to minus 5 by 2 less than that constant value. That constant value on the right. Okay, Pt, from this equation you have Pt raised to minus 5 by 2 equal to a constant because this is theta of 5 by 2. When t greater than Tc, that becomes g 5 by 2 of z, and its value is always less than theta of 5 by 2. That means Pt raised to minus 5 by 2 is less than the constant value when t greater than Tc. What is less than the constant value means P should increase or T should decrease. Okay, for if you consider the value with this graph, then for getting a value less than this constant value, either P should decrease or T should increase. That is, in this graph, this region P decreases means the right side of transition line, or T increases means also the right side of transition line. Left side of transition line is not allowed because this value is always g5 by 2 z is always less than this constant value. So right side is not allowed. On the line transition line you have mixed phase. Sorry, left side is not allowed. On the transition line you have mixed phase, and the right side is normal phase alone. Now we will calculate the specific heat. We have the internal energy U equal to 3 by 2 PV for a Bose gas. This equation we proved in the last class. So we can write it as 3 by 2 into P is Kt by lambda cube G5 by 2 of Z, and there is a V also. So this is 3 by 2 KTV by lambda cube G5 by 2 of Z. The previous graph, that is this one, depicts the variation of PV by NKTC versus T by Tc. Okay, this equation, so U is PV, that means that graph shows equally well the variation of U with the T. Okay, the variation of U with the T will also have the same nature. So the graph, the slope of the graph is a measure of Cv, because specific heat at constant volume is nothing but dou U by dou T at a constant volume. Dou U by dou T is the slope of U versus T graph, and U versus T graph has the same nature as this graph. So the slope of this graph will give you the specific heat. And this green one is the actual graph for Bose gas, and you can see that the slope goes on increasing up to T equal to Tc, and then the slope decreases and finally tend to a constant value. So the behavior of Cv is, at low temperature, Cv is vanishingly small. It increases steadily up to T equal to Tc. After Tc, it decreases and tending asymptotically to the constant classical value 3 by 2 Nk. Okay, that is the nature of specific heat. Now we will discuss the different regions. First, we will consider for T less than or equal to Tc. Okay, below critical temperature. Cv by Nk. is 1 by nk into dou u by dou t at a constant n and b. Because Cv is dou u by dou t at a constant n and b, I divide it with an nk. That is equal to 1 by nk dou by dou t of u is nothing but 3 by 2 pv. For t less than or equal to tc, pressure is given by kt by lambda cube theta of 5 by 2. Theta of 5 by 2. This is nothing but the value of g 5 by 2 z, that is z equal to 1. For t less than tc, we can take z as 1. So substitute for this p, you will get it as Cv by Nk equal to this 3 by 2 will come outside, and V you can take it outside because this is at a constant N and V. So there is V by N. K you can take into the inside. So P by K, instead of P by K you have T by lambda cube theta of 5 by 2. Theta of 5 by 2. You have to take the derivative with respect to T. There are two terms which contains T. One is this T itself, the other one is lambda cube. So you can take theta of 5 by 2 outside, 3 by 2 V by N theta of 5 by 2 into d by dt of t by lambda cube. You can replace this partial derivative with the total derivative because this has only t dependence. This you can write it as 15 by 4 theta 5 by 2 d by lambda cube. Why? Because d by dt of t by lambda cube, you can write it as 1 by lambda cube into derivative of t, that is 1, plus t into derivative of 1 by lambda cube. That is nothing but minus 3 by lambda raised to 4 into d lambda by dt. What is d lambda by dt? It is h divided by root 2 pi mk into minus 1 by 2 t raised to minus 3 by 2 into 1 by lambda. Okay. So you can calculate the value of, you can substitute value of lambda here and you can take the derivative with respect to t. You will get something like this, and substituting this value here, you will get it as 5 by 2 lambda. 5 by 2 lambda cube. Substitute for this d by dt of t by lambda cube, you will get 15 by 4 theta of 5 by 2 v by lambda cube. Okay. Now, from this expression, it is clear that Cv is proportional to t raised to 3 by 2 because 1 by lambda cube is proportional to t raised to 3 by 2. All the other terms are constants. So, Cv is proportional to t raised to 3 by 2 for t less than or equal to tc. At t equal to tc, you can write Cv by Nk as 15 by 4 theta of 5 by 2 into 1 by theta of 3 by 2. Why? Because you have here the term v by lambda cube, and v by lambda cube is nothing but 1 by g 3 by 2 of z, but z value is 1 for t less than or equal to tc, so that will give you a value of 1 by theta of 3 by 2. Okay, so at t equal to tc, this is the way in which you obtained v by lambda cube as 1 by theta of 3 by 2. Okay, these expressions we already discussed. And by substituting the value of theta of 5 by 2 and theta of 3 by 2, you will get Cv by Nk as 1.925. 1.925. What is the classical value? It is 1.5. Cv is 1.5 Nk. 3 by 2 Nk is the classical value. It is higher than the classical value. At t equal to Tc, the value is higher than the classical value. Now, for t greater than Tc, Cv by Nk is given by 1 by Nk into dou u by dou t at a constant n and b. Substitute for u 3 by 2 pv, then dou by dou t of 3 by 2 into, take this nk into the bracket, you can write it as t by lambda cube g 5 by 2 of z and 1 by lambda cube g 3 by 2 of z. You can write it as the ratio of these two terms. Okay, you can refer the starting equations of this lecture, then it will be clear. So Cv by Nk equal to dou by dou t of, this is 3 by 2 t, lambda q will cancel, g 5 by 2 z by g 3 by 2 z. Okay, now Cv by Nk equal to 3 by 2 into, you have to apply product rule. You can take 3 by 2 outside. First you take the derivative of t keeping this constant, then keeping t constant, take the derivative of this terms. Okay. Now 3 by 2 into g 5 by 2 of z by g 3 by 2 of z plus 3 by 2 t into dou by dou t. I can replace it with the dou by dou z multiplied with dou z by dou t. Okay. So that becomes 3 by 2 into g 5 by 2 of z by g 3 by 2 of z plus 3 by 2 t. Now this term you have to apply again product rule. Take 1 by g3 by 2 of z as constant, dou by dou z of g5 by 2 z minus g5 by 2 z as constant, 1 by g3 by 2 z derivative is minus 1 by g3 by 2 z square into dou by dou z of g3 by 2 z multiplied with dou z by dou t. But we have this expression n minus n0 by v equal to 1 by lambda cube g3 by 2 of z. For t greater than tc, n0 is 0. So this becomes n by v is small n lambda cube. N lambda cube equal to g3 by 2 z. Therefore, dou by dou t of g3 by 2 z, you can write it as dou by dou t of n lambda cube. So this is n into 3 lambda square dou lambda by dou t. Dou lambda by dou t is nothing but minus 1 by 2 lambda by t. So this is minus 3 by 2t g3 by 2 of z. Okay. Lambda is h by root 2 pi m kt. This step is very simple. You can calculate easily this step. So this is minus 3 by 2t g3 by 2 of z. Also, dou by dou z of g3 by 2 of z. That is dou by dou z of g3 by 2 z is z plus z square by 2 raised to 3 by 2 plus z cube by 3 raised to 3 by 2 plus etc. Take derivative. This becomes 1 plus z by 2 raised to half. 1 2 will cancel. This z square has derivative 2z. 1 2 will cancel. Becomes z by 2 raised to half. Z square by 3 raised to half plus etc. And this is, if you multiply with a z, z dou by dou z of g3 by 2 z becomes z plus z square by 2 raised to half, z cube by 3 raised to half plus etc. This is nothing but g half of z. G half of z. That is, you have dou by dou t of g3 by 2 z as minus, you have here minus 3 by 2t g3 by 2z and z dou by dou z of g3 by 2z as g half z. Divide those two expressions, you will get it as minus 3 by 2t g3 by 2z by g half z. Here, this left hand side you can write it as 1 by z into 1 by z into dou z by dou t. Okay, because dou g3 by 2z is both there in the numerator and denominator. So you can write this left hand side as 1 by z dou z by dou t equal to minus 3 by 2t g3 by 2z by g half z. Okay. Now, dou by dou z of g5 by 2z. Dou by dou z of z plus z square by 2 raised to 5 by 2 plus etc. When you take derivative, this becomes 1 plus z by 2 raised to 3 by 2 plus z square by 3 raised to 3 by 2 plus etc. So you can write it as g3 by 2z divided by z. Now you can substitute all this back in the original expression. Cv by nk equal to 3 by 2 into g5 by 2z by g3 by 2z plus 3 by 2t into 1 by z g3 by 2z by g3 by 2z. That will be the first step. Minus 1 by g square 3 by 2z into g5 by 2z into 1 by z g half z into outside you will have minus 3z by 2t g3 by 2z by g half z. Okay. So Cv by nk becomes 3 by 2 into g5 by 2z by g3 by 2z. Here you will have this will cancel and this term z will cancel. You will get it as minus 9 by 4 g3 by 2z by g half z and the last term will give you plus 9 by 4 g5 by 2z by g3 by 2z. Okay. So you can write it as Cv by nk equal to 15 by 4 g5 by 2z by g3 by 2z minus 9 by 4 g3 by 2z by g half z. This equation is valid when t greater than tc. Now, for z equal to 1, that is for t equal to tc, z becomes 1. G of 3 by 2 of 1 is 2.612. G of 5 by 2 of 1 is 1.34. G half of 1 is actually infinity. Okay. When you put in this expression, when you put z is equal to 1, this will diverge because the denominator is very small and the numerator rises very fast. So this term will diverge for z is equal to 1. But if the denominator is like 2 raised to 3 by 2, 3 raised to 3 by 2, etc., that is for g 3 by 2 z, for z equal to 1, it is finite. But for g half z, it will diverge. So g half z is infinity, so this will vanish. Equation will be 15 by 4 into, you will get this value 2.612 divided by 1.34 and that is exactly 1.9 1.925. So if you find the value of Cv by Nk at t equal to Tc, it will be exactly the value obtained earlier. That means the graph of Cv by Nk is continuous at t equal to Tc. When you calculate Cv by Nk from upper bound and from lower limit, both will result in the same value. Okay, so you can say that Cv by Nk is continuous at t equal to Tc. Now, for t tends to infinity, what will happen? All this g5 by 2 z becomes z, g3 by 2 z becomes z, g half of z becomes z. All this becomes z. And if you substitute this as z, this will be 15 by 4 minus 9 by 4, and that will be 3 by 2. So it is the classical value. It is the classical value. So this is the behavior of Cv by Nk versus T by Tc. At t equal to 0, it is 0, then it increases steadily up to a value of 1.925, then it decreases and saturates to a classical value of 3 by 2 N. This is the behavior of Cv for a Bose gas. For a Boltzmannian gas or classical ideal gas, you have Cv is equal to 3 by 2 Nk always. But for a Bose gas, depending on the temperature, it will vary, and the nature is something like this. You can see the experimental plot of specific heat versus temperature for liquid helium 4. Okay, this is an experimental plot, and the similarity of this plot with this curve prompted F. London to suggest in 1938 that the curious phase transition that occurs in liquid helium at a temperature of around 2.19 might be a manifestation of Bose Einstein condensation taking place in the liquid. Okay, and if you substitute the value or data for liquid helium, namely the mass m equal to 6.65 into 10 to the power minus 24 gram and v equal to 27.6 centimeter cube per mole, we obtain a Tc value of about 3.13 Kelvin. Okay, from the equations obtained by this treatment, ideal Bose gas treatment, if you calculate the Tc value for liquid helium, you will obtain it as 3.13 Kelvin, and the experimental value is 2.19 Kelvin. Okay, so it is not drastically different from the observed transition temperature of the liquid. Now, I will give you the condition for volume for the onset of Bose Einstein condensation. We already have for Bose Einstein condensation n greater than V into 2 pi m kt raised to 3 by 2 by h cube theta of 3 by 2. This is the condition in terms of number of particles. We are looking for a condition in terms of volume. So you can write here V by n as h cube by 2 pi m kt raised to 3 by 2 into 1 by zeta of 3 by 2. That is V by n less than lambda cube by zeta of 3 by 2. V by n is nothing but volume per particle, that is less than lambda cube divided by zeta of 3 by 2. This is the condition for the onset of Bose Einstein condensation. Okay, so let's define this limiting value as Vc, the characteristic volume, that is given by lambda cube divided by zeta of 3 by 2. Then we can see that if V is less than Vc, then we will have Bose Einstein condensation. If we are fixing the number of particles and temperature and vary the volume below a particular volume called Vc equal to lambda cube by zeta of 3 by 2, we will have Bose Einstein condensation. Keeping n and t fixed, if we vary the volume, when volume is less than this particular volume, lambda cube by zeta of 3 by 2, this is actually volume per particle, then we will have Bose Einstein condensation. And this critical volume is proportional to T raised to minus 3 by 2. T raised to minus 3 by 2. Also, for V less than Vc, that is when we have Bose Einstein condensation, the pressure is given by P0 equal to Kt by lambda cube zeta of 5 by 2. And we already mentioned that it is independent of V, that is infinity compressibility. And we can multiply those two quantities P0 Vc raised to 5 by 3. Okay, we already have an expression for P0, we already have expression for Vc. Then P0 Vc raised to 5 by 3 will be Kt by lambda cube, zeta of 5 by 2 into lambda raised to 5 divided by zeta of 3 by 2 raised to 5 by 3. So we can write it as Kt into zeta of 5 by 2, zeta of 3 by 2 raised to 5 by 3 lambda square. So this will be a constant value. Okay. P0 into Vc raised to 5 by 3, if you calculate that value, that becomes a constant. There is no T dependence, there is no N dependence. All these quantities are constant. That means P0 Vc raised to 5 by 3 is a constant. At T equal to Tc, we have the critical volume and this pressure. So P0 into Vc raised to 5 by 3 will be a constant. So you can look at this plot. This red line shows the transition line and is the graph of PV raised to 5 by 3 is a constant. If you take at a particular point for which pressure is P02, then the corresponding volume we can term as Vc2. Then this P02 into Vc2 raised to 5 by 3 will be same as P01 Vc1 raised to 5 by 3. Okay. So this means that it is not PV raised to 5 by 3 is a constant. It means that P0 Vc raised to 5 by 3 will be a constant. This graph is actually the transition line PV raised to 5 by 3 is constant. And if you take any points on this graph at the critical temperature, then we can say that P02 Vc2 raised to 5 by 3 or P01 Vc1 raised to 5 by 3. All these are the same. All these are the same. And the left of this transition line represents the mixed phase and the right side represents the normal phase alone. Okay, this graph, this line is not possible one. Okay, this is actually PV raised to 5 by 3 is constant. For Bose gas, PV raised to 5 by 3 is not a constant, but P0 Vc raised to 5 by 3 is a constant. Okay, so the left side of this transition line represents mixed phase and the right side belongs to normal phase alone. Thank you.